this example, right, of this last loading example. Did we not finish that?
The last thing I have is sine natural frequency t times 2 cosine 0.5.
We're expanding.
108.
Oh, okay, so we were going to find the maximum displacement, right?
Yes.
Okay, okay. So let me summarize that then. We had this loading, okay, T0 over 2, T0, 0. T0 was 0.031 seconds. So we derived the natural frequency, which was 34.01. The stiffness, if I remember, was 3 times 10 to the 5 pounds per inch. What else?
Wasn't natural frequency 31.05?
31.0 maybe? I don't know, I'm just,
I have 34.05.
34 is, okay.
Yeah, that's what I have as well.
Okay, ladies, per second. So this was the loading, and then we wanted to find the maximum displacement, right? So we derive U of t for each case, right? Case 1, case 2, case 3, by, of course, using this Duhamel integral, right?
Okay.
So let me just refresh your memory. So we use this for each case. We set up this function. We had 3 regions, region 1, region 2, and region 3. So we derive these, the displacement function for each case. And as I said, in order to find the maximum displacement, we need to take the derivative of u, equate that to, with respect to time, equate that to 0 to find the time at which this is maximum. But as we did that, we realized that the derivative here stays positive. Here also the derivative is positive, so we could not reach the maximum in those 2 regions. So we concluded that if there will be a maximum, would happen in this region, for which the displacement function was, as we had derived that, the displacement function for region 3 was 2f naught over k t0 omega n times 2 sine omega n t minus t0 over 2 minus sine omega n t minus sine omega n t minus t naught, right? And then, as you just mentioned, we just expanded these terms and simplified that, and resulted this part in the bracket resulted in this expression, which I'm not sure if I simplified that or not, but it will give me, by realizing that, of course, for instance, if you expand this, you have 2 sine omega n t cosine omega n t0 over 2 minus 2 cosine omega n t sine omega n t0 over 2. And same thing here. These are just numbers, right? We have those values for omega n, for t sub 0. So substitute those in there, and we, summarize the result as this. Becomes cosine 0.5108, which is omega n times t naught, minus 1 minus cosine of 1.021 0.16. This is actually omega n t naught. This is omega n t naught over 2 evaluated. Okay. Then plus cosine omega n t times minus 2 sine 0.5108 plus sine of 1.0216. So, in other words, if you do these calculations, simplify this, you basically will get 2f0 over k t naught omega n times 0.2227 sine omega n t minus 0.1248 cosine omega n t. So this is the simplified version of the response in this region. As we said before, in order to find the maximum displacement, you have to take the derivative, equate that to 0, find the time, substitute it back into this equation. But since we do know now that if a maximum displacement occurs would be in this region, and this equation was simplified in this form, you can easily see that these two functions, yes?
I was gonna ask, so the 2 force over the kt omega n is omitted at the top part of the equation, right? For the
That's this part, right?
yeah.
Right.
Yeah.
So I took basically sign off. That's
No,
one.
not the sign out, but the 2f naught.
Oh, yeah. No, I'm just
Yeah.
evaluating for it here. I'm just evaluating this, whatever is in
Okay,
this bracket,
yeah.
right?
Just compare.
Now the complete UT, in other words, this is just that bracket, which is this part, right? Now U of t is this, right? If you look at this, you can immediately see that this can be converted to a single harmonic function, right? In other words, this is what? If this is A, this is B, we know by now, you can basically write this as something like this, right? So instead of taking the derivative of this, equate that to 0 and find, that way we want to find maximum displacement. We see that the response is basically a harmonic function. So if it is going to be maximum, or to find its maximum value, that maximum value would be just this amplitude times this, right? So in other words, U max then would be simply 2f0 over k t naught omega n times the square root of 0.2227 squared plus 0.1248 squared. So you just substitute here for F naught, which is 100,000 pounds. K was given 3 times 10 to the 5 pound per inch. And T naught was 0.03, and omega n was 34.05 radians per second. If you substitute those in that expression, you get Q max is 0.167 inches. Okay. Now we make an observation. If you look at this, okay, which is the static displacement, you see that F0 over K, if you just put these numbers in there, would be about 0.33 inches. That means it proves again that what I mentioned before, that in the case of short duration loading, versus in this case of a blast loading. The maximum response is not necessarily worse than the corresponding static displacement. In fact, in this case, as you can see, the maximum dynamic displacement is almost half the corresponding static displacement. So the reason for that is that the maximum displacement under any kind of short duration loading, which we call that shock loading, okay, is a function of two variables: time duration of the load and the natural frequency of the system. Depending on these two, you may have a response that is worse than the corresponding static displacement, or in fact less severe. The point is that contrary to the common assumption or perception that if you have dynamic loading, okay, let's take a factor of safety of 2. That's just not right. It's only that factor of 2 is only valid when you have impact loading. So for other types of loading, you really need to know or evaluate the maximum value, okay? And that was really the main reason of going over this example. This, in fact, introduces us to a concept that I'm going to cover in a minute, and that is called shock spectrum, or response spectrum. Remember in the harmonic loading, what we did always to find the maximum response, we had a tool. Dynamic response is maximum dynamic response is the maximum value of the frequency response function times the static displacement. We saw here that that doesn't apply here, and in general we have to really go through the pain of, for each region of loading, find the maximum displacement and so on. But based on this observation, and realizing that the maximum displacement is really only a function of two variables. These are the critical parameters that contribute to maximum displacement: duration of the time and natural frequency. We introduce a concept which is called shock spectrum. In other words, in practice, the maximum displacement as a function of the time duration and the natural frequency of a system is plotted, and we'll study that, and we call that response spectrum. Before I get to that, I had promised you that I would just conclude Duhamel integral by introducing a general approach which doesn't require you to go through all these pains to find a response, especially in the case that even the function might be such that is not included in one of those tables that I gave you, and that is called numerical. The general approach is numerical integration. In other words, in practice, in order to find the response under general loading, it's not easy to use these analytical solutions or, basically use any of these tables that are limited in terms of the type of function you have. The most general approach is numerical integration. What is numerical integration? If you look at the Duhamel integral, whether you consider the undamped case or damped case, for instance, for the undamped case is what? Is 1 over m omega n integral from 0 to t of f of tau sine omega n t minus tau d tau. For the damped case was similar, more complex, 0 to t of f of tau e to the minus zeta omega n t minus tau sine omega d t minus tau d tau, right? And this one actually can be written as e to the minus zeta omega n t divided by, right, by e to the zeta omega n tau. Okay, but anyway, if you look at these two integrals, in general, if you have a function like f of tau that is complex, is not easy to basically find an analytical form for that and so on, this is what we do. I would just, let's focus on this one. You can see that since tau is a dummy variable, if you expand this term, in general, you have what? You have sine omega n t cosine omega n tau minus cosine omega n t times sine omega n tau, right? So this can be then written like this. Since sine omega n t is really the sort of the constant variable is tau, take that out of the integral, you have what? You have 1 omega n sine omega n t, right, times the integral from 0 to t of f tau, okay, cosine omega n tau, t tau, minus 1 over m omega n cosine omega n t integral 0 to t of f tau cosine f tau sine omega n tau d tau. So if you look at this, if I call this, say, A, and this B, right? Isn't that interesting? U is always what? U is always a harmonic function, right? If I write it like this, that A sine omega n t minus B cosine omega n t. Of course, A and B are time dependent, right? But nevertheless, this is basically something like this, right? It would be 1 m omega n, right? A squared plus E squared sine of something, right? This is really the foundation for the general form of way of solving Duhamel integral. Because all you have to do is perform these integrations. In other words, find A and B. Of course, it's not easy because it depends on this function. F of t can be discontinuous, can be of all kinds of shapes, right? So there are procedures to do that. And we call those numerical integration procedures that maybe someday you come across that if you have taken a course, maybe finite element. There are some numerical procedures or numerical analysis approach. These are some of the most common type. For instance, central difference method, if you use, basically instead of time, we'd go difference equations, use that. Another approach is, which is commonly used, is Newmark beta numerical integration or Wilson theta scheme for numerical integration. We don't study any of these. If you're interested, you can take the second course or in some numerical analysis course, we'll see that. But the point here is that, in general, that is the approach. We use numerical method approach to evaluate these integrals, but at the end, Duhamel integral is reduced down to nothing more than a harmonic function, except the amplitude is time dependent. Yes?
What would be inside the sine function?
It's signed like the usual things, right? You know, if you have, you will have something omega and t plus some phase angle, right?
Oh.
Right. So, because omega n still is the frequency of this. That's why, in fact, in this form, you see that even more clearly that Duhamel integral is, or the response due to general loading, is always a function of natural frequency and, of course, time duration, which is hidden in this. Okay. So with that said, this is Duhamel integral. It's really, but this numerical integration in itself is a very fascinating area. We don't cover it here, but you can use, of course, you guys are good at it. I mean, you can use all kind of MATLAB tools, and because numeric beta and the Wilson theta have, there are in fact MATLAB modules have already been incorporated, and you can use those if you're interested. I always tell a story about Professor Wilson and Professor Newmark. The reason for that is, first of all, I had the honor of being a student at the University of Illinois when Newmark was the department chair of civil engineering. Newmark is a giant in earthquake engineering field. He's one of the founding fathers of earthquake engineering, And I told you once maybe a story about him designing that 42-story building in Mexico, but he's made so many contributions in so many fields. So it's quite something. So Newmark beta is a very powerful method that is used in finite element especially. Wilson is another, I would say giant. He's one of the founding fathers of the field of finite element. There are a few people you can consider as the fathers of the field of finite element. Zinkewicz in England, Wilson, Dick Gallagher, and Clough. Wilson was a professor at UC Berkeley. He had a student by the last name Barthet. I don't know if some of you have taken the course in finite element might have seen the book Finite Element by Barthet. He's a professor at MIT. He was a student of Wilson. So the first book, one of the earliest book in finite element that came out was authored by Wilson Barthet, Finite Element book. When Wilson retired, somehow the book, of course, was revised a little bit, was changed to Barthet. Well, let's get to the last topic I'm going to discuss, and that is response or shock spectrum. So as I said, in harmonic loading, Umax was easy, was the static displacement times the maximum value of the frequency response function, okay? Sort of an equivalent of that is response or shock spectrum, which is widely used in practice to find the maximum displacement or the effect of the general loading, like shock loading and so on a system. Let's demonstrate that the concept through the example that we did. Let's look at this simple example first. We have something like this, right? if you look at the response for the period that the maximum response occurs, was something like this. Maximum response was F0 over K, and intentionally I write it like that, times T0 omega n. We just did that, so it's still fresh. 0.227 sine omega n t minus 0.1248 cosine omega n t. Okay? If you plot this way, if you make a plot that the x-axis is this parameter, which is time duration over the natural period of the system. In other words, t is 2 pi over omega n. And this is the normalized value. In other words, this is u max over f0 over k. You see that if this is f0 over k, if you plot this, it would look like something like this. We call this shock spectrum. In other words, this is the plot of the maximum response versus basically a normalized time duration over the natural period of the system. This has actually quite application. Let me, for instance, look at, for the specific case, T0 was what, 0.03, and the natural period was, natural frequency was 34.05, so 2 pi over that would give you 0.1845, okay? So for this case, T0 over T is what? Is 0.1626. So that shows the value of this curve. That if you plot that function in the general form, which is this, from this function, given the time duration and the natural frequency of the system, which is 0.1626 here, you just go up here, and you can quickly evaluate, this becomes 0.5. So the response spectrum is a plot that can give you quickly the maximum dynamic response. For instance, for this case, these specific values are, if you plot this curve for a loading like this in general, which is what we did, you see that at the value of 0.4 for T0 over T, you will get a response which is equal to the static displacement. Or in other words, you can conclude that if you have a shock loading which looks like this, okay, as long as this T0 over the natural period is less than or equal to 0.4, the dynamic response would never exceed the corresponding static displacement. Or here you see that for T0 over T, which is 0.8, you have the maximum, the absolute maximum dynamic response. Okay? So from this curve, you can do a lot of things, because by using this, you can immediately find out what are the critical values. For instance, if you have a shock loading like that, what would be the critical time duration. Of course, normalized versus natural period of this system. But, or you can see that beyond 0.8, no matter what this t value is, the maximum response, this is about 1.25, okay? No matter what, if you exceed 0.8, maximum response would always oscillate around 1.25 and 1, okay? So in other words, for the design purposes, you know, you could not expect more than 1.25 as far as the maximum response goes. So this is called shock spectrum. You can plot, these shock spectrums are plotted for a wide range of short duration loadings, and by plotting those, you can use them for all kinds of practical research purposes to find the maximum displacement in the system. Yes?
In the U max equation at the top, so why is the max further up?
Further up,
Further up?
the top equation,
The
so,
top of- yeah.
You mean this one?
no, the top equation on both.
This one?
Yeah, that's the question. The t inside the sign, so how is U max a function of t if it's the max?
Oh, the U max is always a function of t, right? In Duhamel integral, is always a function of t, right?
Isn't it the maximum of all time?
Right, it is, but you know, if, as we derive that, right, we realize that the maximum, oh, you're talking about the absolute value, right? We are talking about this function that we're plotting, I'm sorry. We're plotting this. This is this times the amplitude of this is the absolute maximum value of the Umax, right?
Is that t supposed to be t naught instead of t?
No, it's actually t. What we did, in order to find the absolute, we're doing is something different. If you want to find the absolute maximum value of U max, which is this, right? We convert this to a harmonic load. The amplitude of that times this was giving us the absolute value of U max, which is only this value. But in general, if you keep it this way, you can see that as a function of time, this U is changing, right? This is, in other words, we are not evaluating the amplitude in this case, right? So it is changing as a function of t. You see what I'm saying?
I'm not sure what I did.
Well, let's talk about that. So with this, I was hoping to actually finish, go through another example, but I think it is sufficient enough. And by next week, we're going to start multi-degree of freedom systems, and hopefully we'll spend 2 weeks on that. But on Tuesday, I will give you your final exam in advance. So we'll have portions on, a good portion of that would be on what we have already covered, but we will start also multi-degree of freedom system. So the final also includes some problems in multi-degree of freedom systems. But it will be due by the end of the following week, which is June 8th. So you don't have to bear with me during the final week. So you can get it done over with by June 8th. Okay. Thank you.